Welcome back to another video, which will be about the second half of Chapter 18, a macroscopic description of matter. My name is Richard, and in this video we will be going over ideal gases and PV diagrams. With that being said, let's begin. Let us first talk about what an ideal gas actually is. An ideal gas is a gas of randomly moving atoms that only interact through elastic collisions. If you remember momentum from Physics 40A, elastic collisions occur when two or more objects bounce off of one another. In this case, the molecules of an ideal gas can bounce on either other molecules or the inner walls of a sealed container. In other words, these molecules do not stick to one another and move freely. Typically, ideal gases can be assumed for the following conditions. First, the density of the gas is low. This means that the volume of the gas molecules must be smaller than the volume of the container. Additionally, the temperature of the gas must be above its condensation point. Remember, from the last video, condensation is the phase change from a gas to a liquid, so the temperature must be higher to maintain its gaseous state. Now that we have covered the basics of the ideal gas, we can proceed to discussing about the ideal gas law. When it comes to any type of gas, there are four state variables or characteristics to consider. These include pressure, volume, temperature, and the number of moles. All of these variables formulate a special relationship, which, in essence, is the ideal gas law. The governing equation is shown here, which is equal to PV equals nRT. Here, R represents the universal gas constant, which is equal to 8.314 joules per mole Kelvin. It is also important to note the units for each state variable are in SI units, which are listed here below. Typically, ideal gases are assumed to be in a sealed container, meaning that no gas molecules can enter or leave the vessel at any point in time. Therefore, the number of moles N remains constant during the entire process. If we know N and R are constants in the ideal gas law, we can rearrange it to be equal to PV over T. If two states, 1 and 2, result in the same constant, we can formulate an empirical relationship as shown here. Let us take a step back and remind ourselves the following equations. First is the ideal gas law. Second is the number of moles, which was mentioned in the previous video. Here, the number of moles equals to the number of atoms divided by Avogadro's number. If we substitute the number of moles into the ideal gas law equation, we can see that there are two constants, the universal gas constant R and Avogadro's number. Combining these two constants results in Boltzmann's constant, which is just another representation of the same equation. It is important to note that the original ideal gas law equation considers the number of moles, and this equation with Boltzmann's constant considers the number of atoms or molecules. Let's change base to introducing the PV diagram. A PV diagram is a visual representation of the corresponding changes between pressure and volume in a system. PV diagrams consist of points with connecting lines. Each point represents a state of a gas with its own values for pressure, volume, and temperature. Although we can see pressure and volume directly on the graph, temperature is not easily noticed and is usually mentioned in the problems. On the other hand, each trajectory represents the intermediary states between two defined states. The trajectories can either be straight or curved lines, depending on the process of going from one state to another. Now that we have explained what PV diagrams are, let us move into talking about the different types of ideal gas processes that can be drawn out from the PV diagram. The first type of ideal gas process is an isochoric process. This simply means that the volume remains constant between two states. If we go back to the equation for an ideal gas in a sealed container, we can simply remove volume out of the equation and obtain P1 over T1 is equal to P2 over T2. Moreover, sketching this on the PV diagram results in a vertical line. This should make sense because the volume does not change, but both the pressure and temperature do. The second type of ideal gas process is an isobaric process. This process states that the pressure remains constant between two states. Once again, returning to the equation for an ideal gas in a sealed container, it becomes V1 over T1 is equal to V2 over T2. If an isobaric process is sketched on the PV diagram, it would be a flat horizontal line because pressure does not change, but the volume and temperature do. Finally, the third type of ideal gas process is an isothermal process, which states that the temperature remains constant between two states. Here, the equation for an ideal gas in a sealed container becomes P1 times V1 is equal to P2 times V2. Because temperature now remains constant, the isothermal process should not have a linear relationship in the PV diagram. In fact, it's rather more complex. It resembles a hyperbolic curve. With increasing temperature, the curve would also be able to move outward. Understanding ideal gases and PV diagrams will be necessary for the next chapter, which focuses on work and thermodynamics. If you have any questions or concerns, please feel free to comment down below or visit us at our office hours. The times will be in the description link down below. Thank you and have a good weekend.